Components and electric currents are heating your printed circuit board. How hot would it get? Would the final temperature be compliant? No data sheet in the world can say that. Our software TRM can do it. Why make it complicated when it can be easy? TRM is a perfect software for thermal and electrical analysis of your Altium Design printed circuit board. Be careful when using design rules, internet sources, or data sheets from suppliers. Every circuit board is unique, as are the circuits. For this reason, electrothermal simulations must be physically and geometrically compatible with your design and the board you're working on. With TRM, you get a user-friendly, powerful, and affordable tool. TRM has a steep learning curve when you first start out. Use the default settings and environments. TRM serves advanced users with specialized procedures and algorithms. I will now hand over the microphone to Dr. Johannes Adam from Adam Research for the live demo. Let us explore just the basic capabilities of TRM using a design that is familiar to every Altium user.
Let's talk about this design. We will bring current from this point somewhere to that point, assign some watts to the components, and perform an electrothermal calculation. This is the 2D view seen from top layer. Our intention is to bring current from this point somewhere here using the 5-volt net. And there are several methods to assign amps to pins and pads. Option 1 is to use the schematics. Let's have a look at the power schematics. And we see here some parameter name TRM, a label 2, and a value minus or negative 2 amps. This means that we are receiving 2 amps in pin number 2, starting anywhere in net 5 volt. I'm opening the LCD panel and we see 5 volt nets arriving at pin number 2 and pin number 15. We assign another parameter called TRM. Pin number 2 delivers 1 amp and pin number 15 the other one. How to assign the parameters? Go to the property table. You create a parameter name called TRM and a value like a string, pin number 2 1 amp, semicolon, pin number 15 the other amp. That's one way to assign the values. The other route is using the parameter manager. The parameter manager is a table containing pins and nets and parts. Here you see what we assigned. We also see another physics variable called the power, 0.5 watts to U6. Now we want to export the data. For the simulator, press a button. The rest is done automatically. I will now import what we exported in Altium. This is quite easy. Just open the wizard, the Altium wizard, and say forward, start import. Data are available. Let us inspect. This is a 3-dimensional model of the board, starting with the top layer and dielectric and bottom layer. Drilled files, red ones plated through holes, black ones not plated through holes, and the components. Intentionally, the z-axis is stretched by a factor of 5 so that we are able to see what happens in between the layers. What else do we have? We imported the layer stack with the thickness of the layers as given in the Altium layer table. We have a bunch of drill files, individual drills, in that case 332 plated and 9 non-plated through holes. All the parameters, the plating, the drill depth, etc. can be modified. There's also actions here in the drop-down menu. Create a pattern out of a parent drilled hole. At the end, the final and most important table is what we call the loads table. This is a list of objects, like the components, and physical definitions like the watts and the amps. This list is starting with the components. Then we have a bunch of so-called pins. Those are the wires. Then we have a colorful table with representatives for the netlist. This object is number 39 of U1, and this pad is member of the ground net. Here we see what we defined in the parameter list in Altium, twice plus 1 amp at LCD1 and negative 2 amp at a connector pad. Data are available in the component list, in the watt column, 1 watt, 0.5 watt. There's a filter where we can rapidly search for the definitions, say amp not equal 0 or watt greater than 0. And all of a sudden we have an overview of the values we defined in Altium. Of course, it's possible to define the values here as well. Let us search for the U's. We want to define another watts for U4 and U5. Let's assume 0.2 watts, and that's it. There are more actions available in this list. Activated by a drop-down list, we can change a bunch of values with just numbers, or copy, duplicate, export, import, and much more. The next step, of course, is to define the environmental conditions. Let's assume a lab temperature of 30 degrees. Calculate. That's it. Start calculation. It will start calculating the electric potential in our 5-volt net, given by the plus and negative amps. The current density is derived, defining the local power in a net. The power of the nets is combined with the power in the components. Finally, we'll come to a temperature. Now let's watch the results. Those plots come for free. It's not necessary to do extensive post-processing. Top layer, dielectric bottom layer. This is interesting, looks like a trace. It is a trace, visualized by voltage. So we start here with negative 2 amps in blue, then changes layer. Current density is like this. There's also some 3D visualization available. And of course, the voltage. And the drilled holes to visualize the up and down of the current in the three-dimensional model. The report file has all results in a table. This file is also available on hard disk. There are much more options than can be shown in this video. For example, transient modes, temperature dependent mode, and a lot of extra stuff.
This was just a brief overview of TRM's capabilities. If you'd like to learn more, please contact us or one of our distributors to schedule an online meeting. You are welcome to submit your own Altium design for discussion. Take advantage of a free trial period. Thank you for your attention.